Hello and welcome to this video where we're going to have a really quick look at some of the quantities associated with motion so that we can go on and have a look in the next video at motion time graphs, so velocity and distance or displacement time graphs. So we're going to have a look at the difference between distance and displacement. So distance is, as you know, is basically how far you travel. Distance is a scalar quantity, so it basically just tells you how far you've moved. So if we start off here, for example, and we follow this path around here, we could simply get a meter ruler or a tape measure and we could measure how far in meters we've gone, and that would tell us our distance. And because it tells us our distance and we measure it with a tape measure, this thing is measured in meters. So distance, as we know, is measured in meters. Displacement is the vector equivalent of distance. So basically what that means is that distance is a scalar, displacement is a vector. The difference with displacement is it doesn't matter how you get from one point to another. So while the distance, we measure basically how many meters are along this path here, displacement simply tells us the distance from our starting point to our finishing point. So displacement is the distance from here to here in meters. So again, displacement is measured in meters. However, it doesn't matter how we got there. So we would simply say that the displacement is so many meters in this particular direction. Here's another example. So the distance, for example, is all the way around here. So again, we could measure that. The displacement, because these are really close together, obviously the displacement in terms of the number is going to be much, much less than the distance. In actual fact, you can get a very strange example where we start off here and we travel all the way around this path like this. And again, we could measure the distance, and the distance might be, I don't know, say 10 meters, something like that. But because we've started off here and we finished at exactly the same place, the distance between where we started off and finished at is 0. So the displacement for this is actually 0 meters. So although we've traveled around here and there's a definite distance, the displacement is actually 0 because we are back where we started from. Now we can then move on and we can calculate how fast we're going. Now again, this is something you met at GCSE. So speed is a measure of how distance changes. So distance, this thing, is a scalar. So that's a scalar. So we'll put a little s there. Because speed depends upon distance, then speed is a scalar as well. So therefore it doesn't have a direction. So speed is quite simply how fast you are going. And this is the equation for speed. Speed is basically the change in distance divided by the change in time. So that's the distance. And that's measured in meters. And this is the time. Like that. Oops. And that's measured in seconds. So speed is basically meters divided by seconds. So it's often written as meters per second at GCSE like that, and at A-level you'll see it written as meters per second, so meter seconds to the -1. So to calculate speed, you simply look at how much the distance changes by in a certain amount of time, and just do distance divided by time. Velocity is basically the same thing, it's an equivalent, but that looks at how your displacement changes with time. So because this thing is a vector, that now if displacement is a vector, then because velocity depends on it, then velocity is a vector. And in the same way that speed is distance over time, velocity is displacement over time. Again, so this is your displacement. And as we've seen, this thing is measured in meters. This is your time. And this, as it is above, is measured in seconds. So again, velocity is measured in meters per second. So obviously it could actually be fairly easy to get speed and velocity mixed up. You just have to be clear in your head which one you're dealing with. The main difference between speed and velocity, apart from the fact they're a vector, is basically looking at how we can tell this is a vector. So velocity, because it has a direction, often has a sign associated with it. So speed, it doesn't matter which way you go. If you go that way at 3 meters per second, or if you go that way at the same speed, 3 meters per second, it's still just 3 meters per second. In this case, if we go at 3 meters per second at a velocity of 3 meters per second that way, then if we go in exactly the opposite direction, because this is a vector, then your velocity in that direction will be minus 3 meters per second, because it's in exactly the opposite direction. So if it's got a sign associated with it, you can be pretty sure that it's velocity. Now, let's do a really quick worked example based on velocity. Here are our two equations. And we're going to look at an Olympic athlete that runs 400 meters. They do it in a new world record time of 40 seconds. So for the duration of the race only, we're going to calculate the average speed and also the velocity. So the speed A. Well, if we look at this, speed equals the total distance you travel. Well, for us that was 400 meters. So distance is measured in meters. So we've got 400 meters there. Divided by the time. Well, time is measured in seconds. So that's our time. So 400 over 40 basically gives you an average speed as they ran around the track of 10 meters per second. Now B is slightly different. So if we think about B, what's going on with B is you start off here on the track, you run the first bend, you go on the back straight, you run the second bend, and you finish back on the home straight here. So you started here and you finished here, so therefore your displacement equals 0 meters. And if we look at this, if velocity is the change in displacement, 0 divided by the time. So we can automatically say that the velocity, which is 0 divided by 40, is quite simply 0 meters per second. So from a velocity point of view, this person ran at 0 meters per second simply because they started off here and they finished off here as well. So the final thing we're going to look at is acceleration. Now acceleration, this is the definition of acceleration. Acceleration is the rate of change of velocity. So velocity is a vector. Acceleration therefore must also be a vector. Now we're going to have a quick look at what happens with when you apply some acceleration to some objects, and what we've got is we've got two objects here that are stationary, and we've got two objects here, and this arrow shows that they're both already moving in this direction, and this is the same but they're moving in this direction instead. So this object is going to accelerate in this direction, and often you see to show that something's accelerating, you put two arrows on it. So you're stood still, this thing accelerates in this direction, so it's going to get faster in this direction. And conversely, exactly the opposite, exactly as you'd expect. If you accelerate in this direction and you're already stood still, then you travel faster in this direction. So you simply travel faster in the opposite direction because the acceleration's in a different way. Now this thing's already moving in this direction. So if it then accelerates in this direction, what's going to happen is this thing is also going to get faster. Its speed and its velocity are going to increase in this direction. So the velocity is in this direction, it accelerates in that direction, so it gets faster in that direction. If we apply an acceleration in this direction, if it's already going in that direction, what will happen is it will speed up backwards. So basically, that sounds really strange. It's going in this direction, it speeds up backwards. Basically what that means is it slows down. So this thing will slow down. Now if we apply this acceleration long enough, what will happen is the velocity will get smaller and smaller and smaller until it eventually gets to 0. It'll then start to accelerate this way. So what we've then got for a very split second is we've got this situation. So for the split second it stood still, it carries on accelerating in that direction, so then it would go backwards and it would accelerate in a backwards direction. So it would actually change direction. These things, basically exactly the same thing is going to happen. So this is already traveling to the left, we make it accelerate to the right, and so we're going to get basically this situation. So it's going to accelerate to the right, it's going to get faster to the right, but it's already traveling to the left, so it will slow down again, and it'll slow down, so its motion to the left will become slower, and eventually it will stop and it will turn around and it'll start accelerating and getting faster in that direction. In this case is basically the same as that case. So it's accelerating to the left, it's already traveling to the left, so basically this thing is just going to get faster and faster. So they're the things that can happen. So acceleration can make two things happen. It can make your speed change, so the size of the magnitude of the velocity can change, but also it can make you change direction. So there are two things that acceleration can do. Basically, it changes your speed or it can change your direction. So acceleration is, if we want to work it out, is defined as the rate of change of velocity, and basically it's given by this equation here. So if we've got an object and let's say it's traveling in this direction and then it accelerates and then it carries on traveling in that direction, but it's now got faster, it will have an initial speed And initial basically just means starting speed. So it'll have an initial or a starting speed. It'll also have a final speed, like that. Okay, so basically its speed has increased. Because velocity is speed in a certain direction, that also means it has an initial velocity and a final velocity. And these things are going to be velocities rather than just speeds. So they're going to have different signs if they're going in different directions. So this is our initial velocity, which is given the symbol u. This is our final velocity, which is given the symbol v. And then this thing, again, as we've seen, is the time it takes for the velocity to change from u to v. Now, these two are both measured in the same thing. These two, as we've seen, these two are both velocities, so they're measured in meters per second. This thing is measured in seconds, so acceleration is measured in meters per second, divided by another seconds, which is basically equal to meters over second. Well, second times second is squared, so you could write like that, or it's often written as meters per second squared, like that. Often at A-level it's written like that, and that's probably the most common way that you'll see this. So if we know the final speed, and we know the initial speed, and we know the time, we can work out the acceleration in meters per second squared. So let's have a quick look at how we would do that. So here we've got a table, and it shows the velocity of an object at certain times. We want to complete this table first of all. So what we're going to do is we're going to look at the acceleration at this point. So if we write down our equation, acceleration is equal to the final velocity minus the initial velocity over the time taken for that change to happen. Well, it's been accelerating here, so what we've got is time 0 and at time after 1 second. And in that 1 second, the velocity's changed from 0 up to 2. So our first thing that's missing, that's this one here. We take the final velocity. Well, the final velocity was 2. We take away the initial velocity, which was 0 here. We divide it by the time it took. Well, it went from 0 up to 1 second. So if we do that, we get 2 meters per second squared. So we can simply write a 2 in that box. For this one over here, so basically at 4 seconds, the velocity was 18, and at 5 seconds, the velocity was 28. So we can do the same thing. So we'll have a different acceleration. So acceleration is equal to the final velocity, which was 28 meters per second squared, minus the starting velocity, 18, over the time taken. Well, again, it went from 4 seconds up to 5 seconds, so that was 1. So 28 minus 18 is 10, divided by 1, 10 meters per second squared. So we could write a 10 in this box like that. So we've completed our table simply by looking at the final velocity minus the initial velocity and dividing by how long it took for that change to happen. So another student comes along and says, okay, so your acceleration in your table is uniform acceleration. State and explain they're correct. Well, for that, we need to know what uniform acceleration is. Basically, uniform acceleration is just another word for constant acceleration. So constant, again, basically just means stays the same. So if you have constant acceleration, it means that the acceleration is the same all the time. Uniform is just another word for saying it's constant. So if you've got uniform acceleration, it says that this person is saying that the acceleration stays the same all the time. So state and explain. We have to do two things if we're going to answer this question. State. Are they correct? No, they are not correct. Why? So the explain part is why. So no, they are not correct because the acceleration changes, basically, and that's all we have to put. So are they right? No, they're not. Why? Because the acceleration is changing, so therefore it's not uniform acceleration. So that was a really quick look at distance and displacement, speed and velocity, what happens when an object accelerates, and then finally how you work out what acceleration is. So that's it from me for now, so thank you for watching and goodbye.